Good morning. Myself, Kil Kumar, and I am presenting my project title Implementation of Rram based error correcting codes. Um, Introduction. This project explores an innovative approach by embedding error correcting codes within the memory itself, specifically using resistive random access memory, which is called as Rram. Our focus on implementing 7,4 Hamming code inside an array, Rram array, so which detects and corrects data, single bit errors in stored data. By integrating error correcting codes at the memory level, you aim to reduce the one human bottleneck by improving the overall system efficiency and enhance fault tolerance. Problem statement. So, as we know, data transmission plays a crucial role in communicating between systems. During this transmission process, various issues can arise, especially noise introduced in the channel. The noise will change the original data, which means information which you sent is not the same which you receive. So, by this, the noise interference, we should be compromised with the data integrity. So to handle this, we are using error correcting codes, and these codes helps detect and correct data by adding parity bits to the original message. And traditional system follows one human architecture which have a separation between the memory unit and the processing unit, which means whenever you want to encode or decode data, the data has to move back and forth. I mean, it should move back and forth between memory and processor, and this constant shuttling of data access causes delays and increases power consumption and complexity. So, to avoid one human architecture, in-memory computing is used, where memory and processing units are located together. And this means the data can be processed directly within the memory itself. So, in our project, we are using Rram for error correcting code. So, why we are using means it is a non-volatile, which means it retains power when the power is off. It supports multi-bit storage and has high endurance, making it suitable for repeated read and write cycles or operation. Methodology. Here we design a behavioral model by performing a Rram using Verilog A and Cadence Virtusa tool. So this model captures switching behavior of memory devices. And after that, you tested Rram design by performing set and reset operations followed by read operation. And this helps in proper switching between the low resistance state and the high resistance state. And after that, we implemented a 7,4 Hamming code for error correction. So for this, you perform vector matrix multiplication with input message applied to the whole line, applied to the whole line, and the generator matrix which was stored in the Rram array. Here in the right side, you can see that the input message code represented as V1, V2, V3, and V4. First, we measure the column currents, also known as the bitline currents, and these currents are converted into the voltage levels and using current to voltage converter, and which is also called as trans impedance amplifier. And these generator voltage levels are applied to one of the inputs of the comparator, while the other input receives a fixed reference voltage, and the output bit reference voltage is the represents the encoded message. uh, for decoding, we use parity check matrix that is stored in Rram array. You perform vector matrix multiply between encoded message and the parity check matrix. Generator matrix. Here you can see the generator matrix which contains identity matrix and the parity bits. Basically, generator matrix is used to encode the message bits. Here we are having 24 possible combinations for the generator matrix, and we use only three possible conditions. Three possible combinations only. Um, uh, you take these possible combinations using the constraint, using some constraints, like the rows of the generator matrix is linearly independent and the G into H matrix should be 0. Here G is the generator matrix and H is the parity bit matrix. Here we can see the Rram model in the right side. We fixed the set voltage to 1 volt, which is used to switch the Rram to a low resistance state, and reset voltage to a -1 volt to bring back to the high resistance state. Here the LRS, here it is 3000 kilovolt and HRS is 30,000 kilovolt. Here we encode a logic 1 using 400 millivolt and logic 0 for floating input. Here we can see the result of testing the Rram model. A plus 1 volt is applied to switch from high resistance state to the low resistance state, and if you divide that 1.1 volt with the resistance which is in the right side, which is transition from low resistance state to the high resistance state, you get a spike of current 360 microamperes, and a 400 millivolt is applied to read the state, and the current is observed as 133 microamperes, and again minus 1 voltage is applied to switch and to switch back to the cell from low resistance state to the high resistance state.
Now, let us implement 7,4 Hamming code into the hardware. For the implementation of 7,4 Hamming code, we have to map the values of generator matrix into the resistance values of this Rram array. We can we can see the architecture here. It is the architecture for Hamming code encoding mechanism. Here we can see that the generator matrix is mapped into these resistance values of Rram. 0 is encoded in the HRS state and 1 is encoded as LRS state in the Rram. And for the word lines, we are applying the message code. These message codes are applying at the corresponding word lines. And here is the trans impedance amplifier. It will take current as input and output it as voltage. And this is the modular 2 encoder. It is the hardware implementation of modular 2 operations. It will output as logic 1 or 0 required for our encoding of the message code. We can see this is simply a vector matrix multiplication using Rram. This can be done in two ways, in the following ways. One, we can use Rram crossbar array, or we can use 1T1R. In the Rram crossbar array, there are again floating mode and grounding mode. What is grounding mode? In the grounding mode, basically what we do is all the bit lines are sensed at a time. This is parallelism. All the bit line currents are sensed at a time. In the floating mode, only one bit line is sensed at a time. So all the other unselected bit lines are left floated. So we can inherently see that in this configuration, grounding mode provides low latency. All the outputs come at a time. While the floating mode, only one bit line is accessed at a time. So it will have more latency, but the area of the peripherals are greatly reduced. Now, this is 1T1R architecture of Hamming code implementation or vector matrix multiplication. Why do we need 1T1R architecture? So in the previous Rram crossbar array, in the floating mode, there is a possibility of formation of sneak path currents. What are sneak path currents? If the bit lines are left floated, some currents may enter into the selected bit lines and may cause extra currents. This can lead to the bit flip problem. It will potentially corrupt the data. So to reduce the impact of sneak path currents, a selector device can be used. Here, the transistor is used as a selector device. It can be made to work in to work as a switch. This 1T1R configuration reduces the formation of sneak paths. So this configuration can result in multiplexing. We can access only one bit line at a time, but also by reducing the sneak path currents. So we can reduce the area. Decoding of the message code word. Choice of decoding configuration. In our project, we tried to implement all the three configurations for the encoding mechanism of Hamming code. We have tabulated all the results of corresponding message bits and its corresponding encoded words, encoded message bits. We have found that for by using floating mode, sneak path currents resulted more and it caused big flips. So it caused incorrect data or encoding of the message. So we used 1T1 or array. While it provided multiplexing option for the bit lines, but only one bit line is accessed at a time. So its latency is more. By using the grounding mode of Rram crossbar array, the parallel operation can be achieved. So we choose this parallel operation for the decoding mechanism also, but we traded with more area. It is our trade-off. Decoding operation is similar to the encoding operation, but at the receiver side. So what happens is from the encoding circuit, we have got 1 cross 7 message bits. This 1 cross 7 message bits is applied to the uh, parity check matrix of the Rram. The parity check matrix values is mapped into this Rram array, similar to what we have done in encoding mechanism. Now, what happens is this decoding schematic, if there is any 1 bit error in the received message, this decoder has to detect the location of the error. So let us take an example. We have received all ones, one 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 from the encoding circuit. So at the receiver side, due to some noise, let the this bit is flipped. So it became 0 instead of 1. Now this decoder circuit has to detect this error. By performing the vector matrix multiplication of encoded message with the parity check matrix, we can detect the location of the uh, error message. This is the trans impedance amplifier and this is modular 2 decoder. It is similar as modular 2 encoder we have used in the encoding mechanism. So this is the crucial part for detecting the correct position of the error. It performs modular 2 operations in the hardware. Now let us look at the peripheral circuits. The first is transimpedance amplifier. This part is the standard transimpedance amplifier. It takes current as the input. This current is come from the bit lines of the Rram array. Now the output of this transimpedance amplifier is the inverted version of uh, voltage values. It will convert the current values into the voltage values, but the output voltage is inverted. So to get the non-inverted output, we have cascaded this inverting amplifier. At this point, we will get negative voltages. By cascading this inverting amplifier, we can get the non-inverting or positive values at the output. So this is the complete circuit for transimpedance plus with the cascaded of inverter, analog inverter. As I have explained in the previous slide, the transimpedance amplifier, it is what written over here. The bitline current is passed to the input of the transimpedance amplifier. This transimpedance amplifier takes input as current, current as input, and converts into the voltage. But what is the problem? The output voltage is inverted. So we cascade an analog inverter at the output to get the non-inverted voltage values.
The second principle that we are going to discuss is modular to encoder. The basic idea of modular to operation is
The output is 1 if and only if there are odd number of ones, and result 0 if there are even. The same principle applies here. This is the truth table for modulo 2 operation. I will explain this truth table in the next slide using schematic diagram. The output of transimpedance amplifier is given as the input to the three comparators as shown. From our observations and based on principle of modulo 2 encoder, we have fixed these threshold values of this, which is the reference of the comparators. Based on the reference values and the input values, the comparator output will be high or low. And here the final message bit will be the encoded message bit that we obtained finally. This is same as what I explained in the diagram as we represent in the text here. Here modulo 2 decoder is similar that of modulo 2 encoder that we have discussed, but with one increased comparator due to increase in the input size in the decoder circuit. Here we can see 4 op-amps and threshold values are fixed same as like encoder circuit, and output will be the syndrome vector which determines the location of error. The same thing we can see here. Here the input message 1010 is fed to the rounding mode Rram crossbar array, and the output we seen as 10101001. This is same as the theoretical value that we obtained for the Hamming code matrix, which is obtained by using vector matrix multiplication. These are the generator and parity matrix that we are used to show the results that we have obtained. This is the message signal that we obtained from the encoder matrix, and we intentionally flipped a bit from the message signal and we fed it to the decoder circuit. We flipped the message signal so that we can verify our decoding circuit is working or not. Here we can see that the output of the decoding circuit is 111, which is the syndrome vector. Here in the parity check matrix, we can see that 111 is the fourth position. So the error will be in the fourth position. If this will be if there is no error in the received message, then the syndrome vector will be 000. Here we can see a few more message combinations and encoded messages, which we will be able to detect the error successfully. Here, this is the heat map for generator matrix, which we have obtained while operating Rram in the floating mode. Here we can see the theoretical and practical currents that we obtained. There is a huge variation from the theoretical current in the practical current due to the sneak paths that we obtained in the floating mode. Here we can see the scattering plot for the same generator matrix for Rram operating in both floating mode and grounding mode. In floating mode, if we see that the practical currents, there is a huge variation from theoretical currents. If you see here, the threshold is 110 volt. There are few currents that crosses this threshold so that they will be decided as logic 1 instead of logic 0, which will be an error that is bit flip that we can see in the encoded matrix. And in grounding mode, the theoretical value exactly matches the practical value, so there will be no problem in narrowing the window. But the problem is that huge peripheral area is required for the Rram to be operated in the grounding mode. As we have seen in the floating mode, there are huge variations. So we came to 1T1R array. Here we can see that the variations from theoretical and experimental are very less, and the same amount of area that we used in the floating mode can be used in the 1T1R array, except for the transistor, which can be scaled almost. This is the scattering plot for the same thing. Here we can see that both the currents are almost matched, so no bit flip will happen. The results for the other generator matrix are uploaded here as a backup. Here we can see for this generator matrix, and for this generator matrix, the scattering plot. Similarly, for another generator matrix, we can see both the heat map and the scattering plot. Similarly, for all other generator matrix in the all 1T1R and all three configurations, we can see we have implemented complete Hamming code that is both encoding and decoding using Rram and successfully demonstrated its working using the results and plots that we shown.